we have Jyotirmay Ramaraju and Murli Krishna Chavali. Jyotirmay Ramaraju is with the X-ray system DGS modality. She is a gold medalist in biotechnology from JNTU University, and she's interested in exploring analytics for the benefits of healthcare systems. And we have Murli Krishna Chavali, who is part of a team that's developing the one-of-a-kind hospital solution. And this solution will enable the patient interaction, a patient data study in such a way that it is remote, cloud-enabled, and cable-less. He holds a master's degree from the VITU University in software systems. And he's also interested in exploring analytics for the benefit of the business. So please welcome Jyotirmay and Ramaraju onto stage.
Thanks for that introduction, Anu. Okay. So today we'll be talking about pneumoconiosis detection and where data analytics can help us solve in this problem. To start with, what is pneumoconiosis? Pneumoconiosis is an occupational lung disease which is generally caused by inhalation of dust. So when a person is continuously exposed to industrial dust and continuously exposed to that inhalation of dust, pneumoconiosis can occur for a patient. And in general, when we see the workflow or the hospital workflow for a pneumoconiosis patient is in the 5 major steps. So initially, when there are some basic symptoms, a person can go to the hospital, and based on the initial doctor diagnosis, so if with the basic symptoms, if he is considered as positive, then the doctor may recommend a chest X-ray. In chest X-ray, it may be a one-shot X-ray, or the doctor may recommend him to attend a CT scan. Once they get those chest images, the radiologist and the doctor goes through them in detail, and then based on if they also detect it as a positive case, then they may recommend some of the pulmonary function tests. These pulmonary function tests are again based on case to case, so the lung capacity, how much he's able to inhale, how much he's able to exhale, all those pulmonary function tests are done. And if it is positive in that case as well, then bronchoscopy is recommended for a patient. Bronchoscopy is a sense where a small trace of lung is actually taken out, and then based on the laboratory test, the patient is either considered as a pneumoconiosis positive patient or a pneumoconiosis negative patient. And then the treatment follows. Now, in this workflow, if we see, there is one key step where data analytics can actually help us solve a lot of problems. Where if you see the chest X-ray, which we have marked there, so what is the process in that one space is the patient undergoes a chest scan. It is normal X-ray image which is obtained, and once the X-ray image is taken, the radiologist individually goes through the different segments of lung and analyzes that data. And based on his observations, then he's recommending it as a positive case or a negative case. This whole workflow can be automated. So if we can use some sort of computer-aided detection system in that space, then we can easily get to a point where we can eliminate a lot of radiologist work. It can be reduced. I mean, the doctors need not spend much time on analyzing each and every X-ray. Because the problem, if you see pneumoconiosis, it is on an average in a year, there are around like 6 lakh patients who may go for screening, and this is the first stage. So if we can reduce some time in that space, it will be a lot of help. So this is what is a problem statement which we are trying to solve, and we see a lot of use of data analytics in this one particular problem. So to start with, what we got the data set where we started working is, if you see on the right side, there are 2 lungs, left and right, and in general, when they are analyzing the lungs for pneumoconiosis patients, they divide it into 6 segments, right 3 segments, left 3 segments. So once the radiologist divides it, and each zone-wise, he keeps analyzing the data. So we got a data set after the segmentation of the lungs. So we have like based on the intensity values, based on grayscale metrics, we got a data set which has 3 zones, complete 6 zones data with 39 features, and around 500 patients we got the data set. So yeah, this is about the overview of the problem, and Murli will be continuing with the approach.
In the approach from data cleaning to data model selection, we have followed 4 phases. First is data cleaning, data pre-processing, followed by training models and model selection. In data cleaning process, it is mainly divided into 2 parts, cleaning the missing data and also cleaning invalid data. So when you talk about missing data can be found in patterns, or they cannot be pattern as well. So it can be completely random, or it can be partially random, or you can find a pattern but you cannot see the consistency in the whole data set. And it can be you can find a proper pattern inside it as well. In our case, it is completely random, so we try to solve that problem by using mirror mode substitution. In mirror mode substitution, whenever there is a missing data, you substitute that value with the mean value of all the data in that particular feature, and you clean that particular part. So by doing this, you make the data more cleaner. And the next part is cleaning invalid data. Invalid data is where, in our case, we have a range of values for some features, and if the values go out of that range, we consider it is invalid. In that case, what we do is we again do a mean substitution so that the data is cleaner. By doing this, as Jyoti said, we started with 500 patients, but it came down to 473 patients and 39 features. There were few rows which had a lot of invalid and missing fields, so we had to remove a few rows of patients as well. So when we come down, it came down to 473 patients. Next is data pre-processing, which is very important part. We have feature scaling and feature selection as part of this. So in feature scaling, in our example, we had features which are ranging from -2, values of these features from -2 to +16, and some go from 5,000 and 6,000 as well. So if you feed these values as they are to the model, then the model efficiency and predictability will go down in a huge level. Then to do that, what you have to do is you have to normalize all these values and bring down in the same scale, so that those values are in the range of -1 and +1. So so to do that, we use mean and standard deviation. There's a formula for using that. So you subtract the mean and divide by standard deviation, and you get the values for that. We use that and we standardize all these features. The next is feature selection. In any data set, from all the features that are present, not everything is completely relevant and not everything is correlated to the actual predictable outcome. So we use principal component analysis in this case to reduce the number of features and to see how significant all those features are in predicting our result. For example, if to see how feature selection is important, if you take age and date of birth in a particular data set, if you have age, you can determine. If you have date of birth, you can determine age. So having those two fields in a particular data set will make the model will make the data set redundant. You have to remove all those values. So by using this, we found all the significant and important features, and we reduced, as you can see in the bottom, for all the different zones, we came down to different number of features for each zone. So by this way, we reduced the input to our model so that it can be more efficient and we can tune it well. The next is the training model. In this phase, all the data we have got, we divided into 3 parts. Training data, test data, and cross-validation sets. So 60% we have taken as train set, 20% as test set, and 20% as cross-validation. Cross-validation is very important because if you only have train and test sets, if you train your model and if you test it and if you see that the results are good, it may not be good because the model that you created may be exactly fitting to that particular data set, which is not a good thing. So what we do is we take 20% out of the whole data set, we take 60% and train the model, and then 20% we test it to see how good the efficiency of the model is. And then you'll use the last 20% as a new data set that is there to see how the model is performing in a new data whenever you have. So that way, we get a stable model after training in this procedure. The last one is model selection. In model selection, we have considered few candidate classifiers like logistic regression, random forest, neural networks, and SVM. Uh, and we got down to SVM. There are many reasons that we have because why we chose SVM. Uh, One of the reasons is SVM, if you compare to neural networks, it is faster to train as the data set is small, and we don't have to train for such a long time for such a small data set. And it is more efficient than logistic regression. The accuracy is better. And the two main reasons why we chose SVM is because SVM has been proved to be better in medical space and in predicting those values. The other one is we can choose different kernels and we can tune it according to our needs, and that is how it is more relevant to our case specifically. So that is why we go with SVM. So this is how we have taken an approach starting from data cleaning till model selection. The results and how we went through, Jyoti will be taking it on. SVM is support vector machine. So it creates a hyperplane among all data points which is farthest from all those data points. So by that hyperplane, how you create, I said kernels, right? So that hyperplane, how you create, is dependent on the kernel that you're using. So when you create that hyperplane, you can tune it much more better so that it suits more to your data set.
So coming to the results and analysis part, for any classifier, if we have to consider the results, the main thing which we see is the confusion matrix. So if you see this matrix, the predicted results and the actual results. So if we predict it is yes, and if the actual result is also yes, then it comes under true positive. If we predict no, and the actual result is also no, it comes under true negative. So in this 4 blocks, the most important thing is I am predicting the patient is suffering from pneumoconiosis, and yes, if the patient is suffering, he'll fall into the true positive. And if I'm predicting the patient is not suffering, and the actual result also is not suffering, he'll fall under true negative. But in most of the healthcare related problems, it is more important to focus on false negatives and false positives. I would say more than false positive, false negative is more important because we are predicting that the patient is not suffering from pneumoconiosis, where the patient is actually suffering. And because of that, the disease may be uncovered at a later stage where the treatment also may not be very useful. So the main idea here is to minimize the false negatives and also false positives, I would say, because we say that the patient is suffering and he has to go to the next pulmonary function test. In that stage, again, I mean, there'll be a lot of loss of money and time as well. But yeah, it is little more acceptable than when compared to false negative is what I can say here. So based on these 4 things, we generally consider accuracy, precision, and recall values for any of the classifier. And so we, as Murli was saying, we took these 4 different classifiers: logistic regression, neural networks, random forests, SVMs. And for these 4 classifiers, we tried to find out the accuracy, precision, and recall values. And these are the results which we have seen. So all these calculations can be done from the matrix itself. If you see. We can go to the next slide. So again, being very specific to our problem, as we have mentioned, we divide a lung into 6 major zones. So even in one zone, if there is a pneumoconiosis nodule, or if we find there is a positive case in one zone, we should, ultimately the patient is suffering, so final result is a positive case. So in such a scenario, such a case which we were considering, it was more important to consider 6 different zones separately and get all those results and put them into one final classifier. So we took SVM for each of the zone, we got those results and we fed it to the final SVM classifier, wherein we are predicting if it is actually a pneumoconiosis patient or not. So this side you have all the 6 individual zone results which we got, and the final results are mentioned for the accuracy, precision, and recall values. So this is about our case study, and yeah, one major conclusion is such data analytics can actually help us in pneumoconiosis detection, wherein we can actually reduce the time for radiologists or the doctors. And also, we have considered like 500 patients, which is a very small data set, I would say, because Every day there'll be around 1,000 scans in a hospital, which the data keeps on multiplying. So for us, the next step is to take a bigger data set and again work on it and continue the analysis. And one more major thing is not just pneumoconiosis, there are many other healthcare related issues, especially if we take any cancer related, breast cancer and all. Screening is the first stage. So during screening time, there'll be huge amount of data, which again individually they'll be analyzing. So in such cases, we can actually recommend such solutions so that the screening time and all that workflow is reduced, and doctors or the radiologists can focus or concentrate on the next set of workflow. So this is what we have from our side. I think we're pretty much on the time.
Yeah.
Okay, any questions now?
Okay. On the very first slide, we saw about the features. So what is that features, 39 features, on what basis we decide that what will be the features?
Yeah.
And how we then categorize that for this particular 6 sections, for first section only 13 features will be applicable, and on second so and so numbers of features will be applicable. How we decide that?
Okay. So first, to answer the first part, it would be like 39 features were taken across. Based on the segmentation, whatever we got for each of the zone, they were 39 features considered, and we got a complete data set. And those features are mainly related to the grayscale values. I mean, once you take an X-ray image, each and every pixel value and the grayscale value, from those, the features are derived. It is mostly the mean and standard deviation of histogram and all that data set. And from that, how we are dropping to set of features is what he has explained in data feature selection and feature selection basically. We use principal component analysis, in which we got this many components from the 39. So in most of the cases, if you see, there may be 10 features and not everything is equally relevant. So first feature may be weighted like 10%, second feature may be a little less weighted. So if you want to get to more accurate results, it is always important to eliminate a few features which are not very relevant to our data set. Now again, this is very specific to the problem you are solving, so individual cases may vary. So if I'm saying in my case I'm getting around 13 features for the first thing, probably if I'm going to increase my data set or select another data set, my model should be in such a way to handle what are the new changes which are bringing in with the new data set. So it is not one thing which is taken across like a standard, gold standard I would say, but depending on your data set, we select what features are more relevant and what features are not more relevant.
Hi, my question is again on the first slide.
Sure.
So it's about the cleaning, the data cleaning. How do you detect the missing data? Basically, if it is not there, the missing part, how do you do that?
Yeah. So we generally take a look at all the records when we go through the data set. So that is one way of doing it. One way is just try to print all the data on screen and see if there are any matrix in a matrix form, if you can print them. What the data that we took was an Excel sheet, so it was easy for us to see any missing values of that, so that we filter them out if there are any blank fields. So that way we find out, and yeah, that is basically how we find out missing.
So basically you're trying to convert that X-ray image to the Excel and then detect?
Yes.
Okay.
So when Jyoti said that we are doing, we get the intensity values and after the post image processing, right? So that is the input that we got, that where we started.
To add on, whatever data we get from an X-ray is that it will be generally in a form of DICOM image. So all those DICOM image, again after segmentation, we got the data set, which is in a form of CSV. So we started working from that segmentation level. But again, you have MATLAB which can read DICOM images and give each and every pixel value if you want to consider the segmentation also in your algorithm. But for us, the problem statement was after the segmented data.
Yep.
Thank you.
Hi.
Yeah, you spoke about precision, recall, and accuracy. So why are those three only important? Why not just precision or only recall or only accuracy? Why do we need all three to predict the...
Good
in the
question. It
classifier?
is not just only these three. If you see, we are evolving in such a way that we have F1 score. We have a lot of other things as well. But to start with, we thought these three are the major ones. So we picked up these three. And if you see in general, any other metrics, any other value which you are going to consider, it is going to come from the confusion matrix. So as I mentioned, false positives, false negatives is what we have to look at. And all these three are also derived from that. So your accuracy is going to vary if your false positives and false
So
negatives.
among these three, which is the most important? Which we
I
need
would
to
say
consider?
accuracy.
Accuracy.
Yeah. At least for our data set, because it is a very small data set, for me, accuracy plays a major role. Because we have like 500 patients, I would focus on some model which will be more accurate.
And
Again,
not more
it made-
precision or recall. Like, so when would you use precision and recall as a major thing for your data set? Or
it depends. Like, again, when mostly precision and recall, it's again dependent on false positive and false negative. So if I'm going to say that I don't want any patient who is not suffering to be considered as suffering patient, then I'm going to focus more on that. But overall, if I'm generally looking at a normal solution, I would consider accuracy as my first step.
and do you all have any cutoff percentage that
There's no cutoff percentage as it is, but most of the classifiers will give you around 90% is what we look at.
Thank you for your question.
I heard you said you have to you have 100% data set and you are reducing that to 80% for predicting and 20% you would test it, right?
So 60, 20, 20.
Yeah, say it like 60% or you're taking 80%. So would it actually, wouldn't it reduce the prediction accuracy? Because I know this way, like at least in the case of logistic regression algorithm, you can take the entire data set and you can use some methods called regularization or something to reduce the variance of your prediction model. So that way, if you reduce, say you have 1,000 samples, you are taking only 800 out of it, wouldn't it actually reduce the prediction accuracy?
I think yes, it will reduce, but the point here is we want to focus more on test and validation data set as well. So we have different ways again, leave one or cross validation, which will keep going through the data set and selecting only a portion of it. We have different methods, but we chose this mainly because we thought it should be, we need a proper testing and validation data set for our case.
So one more problem, if I were to add to Jyoti, if you take full data, you might be tuning, even when you say logistic regression, you are saying normalization, you take bias, variance, all these parameters. You have to tune these particular algorithm or model so that you have to also make sure that whatever you're tuning is not overfitting your data. It's not going that way. So in order to do that, we just divide into 60% and then we try to tune that part only. It's not like we are losing a lot of data. We're losing some percent, but we are also seeing how good the accuracy is. So that is more important rather than if we cannot overfit the model and we can go and...
Right. So generalizability over accuracy. So thank you very much, Jyoti and Murli.
Would like to welcome our next speaker, Priyadarshini Pai, who is a research scholar. She's a research scholar in biotechnology. She's currently pursuing her PhD under the supervision of Dr. Sukanta Mandal at BITS Pilani, Goa campus. Her work primarily focuses on analysis and identification of protein interaction sites using supervised machine learning approaches. Some of the relevant areas where she has contributed are enzyme catalysis, protein small molecule interaction, protein carbohydrate interaction, and protein-protein interactions. And Priya will be taking any questions that you all have towards the end. Now let's put our hands together to welcome our budding scholar, Priyadarshini Pai.
Hello everyone. Thank you Geeta for the kind introduction, and thank you ABI and Grace Hopper Celebrations India for having me here. Coming from hardcore experimental biology to computation in the last 4 years at the Annotate Biomolecules Computational League Group at BITS Pilani, it has been a tremendous journey, and I'm here to share some glimpses of the same. I hope you'll enjoy my talk. Before getting into biomolecular interactions, I'll give you a brief context with a daily example so we connect to whatever I have to present here. So we have a child who's in the identification process of a dog, and we have this learning process as guided or unguided. If, say, for example, the child is being taught by a parent and a teacher, then this process becomes supervised learning. Okay? So we have, say, for example, some animals from among which the child needs to identify the dog. Then the dog becomes the positive class, and the rest of the animals become the negative class. Okay? And obviously, the child needs to identify the dog based on some properties or characteristic traits. So then these traits become our attributes of features, okay, for the learning process. And then if we have the child to identify a dog from the rest of the animals, then this becomes a classification problem, a binary classification problem. And if the child is identifying these animals as dogs, cats, and say for example, fox or cows, then these become a multi-class problem. Okay. So coming back to biomolecular interactions. Biomolecular interactions, by that we mean proteins. Have you heard of proteins? Okay, so proteins, carbohydrates, nucleic acids are all biomolecules. They interact, and their interplay is very important for determining the health and disease states of organisms. Okay? And disruptions of these interactions can lead to an imbalance. Okay? And this imbalance may be manifested as diseases. So now let us look at this image on the left. Okay, you have an HIV infection in the blood. You have the germ over there, and you have different cells, and these cells are interacting. So when we talk about host pathogen interactions or infection by different organisms, we're actually looking at these interactions at the cellular level. Okay, so to the picture on your right, you have that microbe, and it is interacting with a certain biomolecule, which is sugar in this case, mannose, and it goes through a series of steps before it is actually presented to the body and eliminated from the blood. So we'll talk about mannose binding proteins today. Okay, and mannose binding proteins, as I said, are very important for recognition of various germs and eliminating them from the body. Okay, so in order to understand how these diseases are developed, we need to know about biomolecular interactions, as I already mentioned, and different experimental and computational approaches are being explored. Okay, so the experimental approaches are very intensive in terms of resources, so people opt for computational approaches these days, and we'll talk more about that in further slides. So this is one of the mannose binding proteins. Experimental studies have shown that it has some activity towards HIV. Okay? So when they do these experimental studies, onto your left there is the structure. So they figure out that this particular organism, that is the plant, snowdrop, has this particular protein called 1JPC as per the PDB code, and it looks something like that. So by the picture on the right, you see that that is a structure, and that is how the protein looks like in the 3D space. Now coming to the 2D space, now proteins are basically a chain of amino acids, and this is how they look like in the primary sequence level. So the first thing that one can get when they have a protein is the sequence. Okay, so some of the residues of the protein are bestowed upon certain properties which help them interact with different kind of biomolecules and execute the function of the protein. So if you look at the sequence, the ones denoted by the capital letters are the interacting residues. So using the sequence information, different state-of-art approaches are available, like Premier and CBS PSSM. They are developed using support vector machines and neural networks. These approaches are state-of-art approaches, and they have limitations in terms of false predictions. And false predictions are a concerning challenge, as they already mentioned. Okay, so now we look at our approach, which is identification of residues involved in protein mannose interactions. Okay, we'll see how we have addressed the issues of false predictions. So as they already mentioned, there are different types of computational approaches which involve training and testing processes, but for developing computational approaches, there is one other method also, which is similarity-based, wherein if you have similar proteins, then the reference sequences can be used to transfer information to the test sequence, or we have de novo methods where you don't have similar sequences, and then you just see different patterns available and try to develop a method. Now, for the method that we have developed, we have used supervised machine learning, and I hope you're all with me with respect to classifier features and data points. Okay, so broadly the approach comprises of two phases, the training phase and the testing phase. Okay, now the training phase has data set from where we extract different biological properties which we encode into numbers and then use these numbers to classify proteins having interacting residues or non-interacting residues. So the problem that we are looking at is if we provide a sequence to the model, then you have each of these residues being scanned, and for every residues, we want to know whether that residue is interacting or non-interacting. Okay, so after we developed the model, we tested on different examples and try to assess how this prediction model works in real life scenarios, and if or not it is serving the essential purposes of reducing the false predictions. Okay, so for our study, we collected 157 protein mannose complexes from the protein data bank that where usually experimental structures are deposited and different informations are annotated over there. So from 157 protein mannose complexes, we divided the data set into two, one for training and one for testing, as I said. Okay, so if you look at this picture, basically this is the gene flow of information that takes place in the cellular level. So you have the gene from where you have amino acids encoded, and from the amino acids, this folding structure is actually how the protein looks at in the 3D space. Okay? So the 157 protein mannose complexes that we had were actually dissimilar. We removed all the similar sequences and checked for any redundancy and fragments or other complexities. And after having made a filtered data set, we looked at different interacting residues. Now, if you look at the picture on the right, you can see there are different amino acids from hydrophobic to hydrophilic. So these are present at the interacting residues. Now, we look at if there is a variation that we can use to discriminate between different types of residues. So if you can see the cysteine represented by C in the picture and methionine represented by M in the picture are not so frequent in the interacting region. Okay, so we wanted to know how these evolve over a period of time and whether this whether their presence in the interaction architecture can be used for discrimination purposes. Okay, so essentially we are looking at the protein as a discrete model where R1, R2, R3 are all the residues in the chain, and the length of the protein is L. Okay, so from the training data set, we extract features. Now for features, as someone already asked, how do we decide on features? So proteins have different properties, different biochemical properties, evolutionary properties, because of which their function is conserved. So we can use these properties actually to discriminate. So the interacting residues have certain properties, like they're more conserved, or they have the requirement of certain biochemistry as opposed to the non-interacting residues. So we can use that to actually discriminate. So here I have used PSSM. PSSM stands for position-specific scoring matrix, and this looks at the evolution of different residues, okay, in the sequence, and S1, S2 are different positions. And if you replace them, I mean the first position, say S1 to 1, if you replace that by one of these, then what is the score? So we are looking at something like that in order to discriminate. Also, it has been reported that not only the target residue, but also the residues surrounding this interacting residues are also important to maintain the neighborhood for interaction, okay, to maintain the architecture for the interaction. So we also look at the neighboring information. So if, say, for example, our target residue is cysteine, represented by C in the right picture, you have the sequence which we cut into fragments, and now we use equal number of residues on either side, varying from, say, 5 to 10 on either side, and then we try to look at the information that we can extract and feed it to the classifier. Okay, so one can use various classifiers like random forest, support vector machines, neural nets, and so many others that are available today. But for the purpose that we are looking at, we want to look at more of the positive region, okay? We are looking at the positive region. This is why the sensitivity and recall are more important. I mean, sensitivity or recall and precision are more important in our study. We want to not miss the positive class, also not predicting too many of the negative class, okay? So this is what we are looking at. I'll just explain these terms in the context of protein mannose interactions. So when we have a residue as interacting and it is predicted by the model as interacting, then that becomes our true positive. Similarly, if we have a residue which is non-interacting and it is being predicted as interacting, then it is a false positive. Okay? Same goes for false negative and true negative. So true negatives are residues which are actually non-interacting, and they are also predicted as non-interacting. From these basic confusion matrix parameters, we actually come to a little more complex parameters called the sensitivity, precision, sensitivity, precision, specificity, accuracy, Matthews correlation coefficient, F measure, and there are so many others of them. Okay, so sensitivity, precision, specificity actually give us information about the positive class and the negative class and how well they are predicted. Okay, accuracy, MCC, and FM, they give us an overall picture. So we get to know what is happening at the larger level. Okay, at both the positive and negative class in a balanced scenario. So we have predicted this architecture. Okay, so we have used this architecture wherein we use the training data set. We do undersampling, which means we select multiple small subsets of negative example along with the positive example, use these classifiers and features, and then develop the prediction models. Then once the prediction is got, then we also use the consensus of these individual predictors and try to see if we can improve the overall prediction performance. Okay, so once we have this prediction model, we test it on the 29 examples that we have reserved for testing. So this was our ensemble architecture. If you look at the training performance, you have these values, and the take-home message from this table is that the random forest in this case is a better predictor or better classifier as opposed to SVM, and PSSM or the evolutionary information is more important as compared to the biochemical information that we have. Okay, so the individual classifiers were stable over different subsets that we have used, and we used some of the best learners and tried to take a consensus of these to test the final 29 examples that we reserve for testing. Okay, so now if you look at these black bars, that represents the consensus approach, and the white represents the performance of the base classifiers. Okay, so individual classifiers are there represented by white, and black represents the consensus. So needless to say, the consensus approach shows better performance than the individual classifiers, and although they are stable, you can actually use the neighborhood information to get more to achieve a better prediction accuracy. Okay, so this, after developing this model, we named this Mowgli. Okay, inspired by the Mowgli character in Jungle Book, that represents the strength of the pack is in the wolf and the strength of the wolf is in the pack. Okay, this is one of my favorite characters, so we just named it after that. And then we also compared it with the state-of-art approaches, which was the Premier and CBS PSSM. Okay, so if you look at the true positive and true negative, you see that the performance of Mowgli is comparable with the state-of-art approaches. Okay, however, if you look at the false positive and false negative predictions, you can see that the performance achieved by Mowgli is much better than the state-of-art because the black bars are much lower than the gray bars. Okay, so with this, we get to know that it is better than the state-of-art. So we pack this up and make it into a software package and make this available for the users. Okay, so the user basically provides a sequence information, okay, from where the PSSM is generated and normalized, after which the feature vectors are presented to the individual classifiers from where the prediction is achieved, and using this prediction, a consensus is drawn and a new class is assigned to each of the residues. So the output looks something like this. On to your left, you have the sequence and you have an annotation for every residue. So the predictor will now predict whether a residue is interacting or not. Okay, so this was the outcome of the studies that we performed. As you know, standalone packages or web servers are very important while developing computational approaches because this helps us reach the users more efficiently. And people who are not from the computer science background, they actually face a lot of problems using these approaches. So they want something more clickable. So it always helps if you have web servers and easily usable software packages. Okay, so some of the other software packages that we have is available at my supervisor's website. Okay, so you can have a look at the protein interaction with proteins, carbohydrates, and other small molecules. Okay, and few areas of research where active involvement from computer science area and biological aspects are also required. Are algorithm development, needless to say. Okay, different algorithms need to be developed to actually solve problems associated with biology, and handling biological data sets is definitely not easy. Although I am from biological background, I get to know that when you encode these into numbers, it is more than just a mundane life of numbers. So when you actually look at these in labs, they are more nicely growing cells secreting some molecules. When it comes to numbers, they get very complicated. Although you want to simplify the problem by making it into numbers, they actually get very complicated. So we need better algorithms. We need to explore applications of these algorithms. We can look into different other features and their encoding. And we can try to explore different discrimination power of the existing approaches and the novel approaches. Okay, if you want to have a look at the more details of this study, you can refer to this paper available. And for more information on the overall aspects of protein interactions and how computational approaches can be useful in this context, and what are the challenges that are associated with it, you can look at the second paper, which will be soon available. So I still have 4 minutes. I can take some more questions. So I have an acknowledgement left. So should I make it later?
Sorry?
I have an acknowledgement left.
Yes, please go ahead.
Okay. So I want to thank the organizers, their exceptional efforts in having me here. I also want to thank my folks back there in the college who have helped me conduct this research very efficiently, and for all you participants who are here and
Thank you. Okay, we have time for a few questions.
I have two questions.
Okay.
One is regarding the PSSM matrix.
Okay.
What is the scoring criterion you used? Means it's the distance between the amino acids or something like that. And the other question is the matrix you used for classification, like accuracy and two different complex parameters. So what is the significance of using these matrix? How they are different from each other?
Okay. So answering your first question, PSSM, you asked me the criteria for scoring, is it? So I don't know, there is no criteria for scoring as such, but we look at the replacement of each residue at the given position with every other naturally occurring residue for that position. So we get to know how conserved the particular residue is in that region. So that gives us an idea of how conserved it is through the evolutionary process. And the more conserved a residue is, it is more likely to be involved in the biomolecular function of the protein. Okay, so that I hope addresses your first question. And coming to your second question, you asked me what is the difference between accuracy, F measure, and MCC, right? So if you look at the formula, accuracy gives you an overall idea about the prediction of about the correctly predicted things among the total things which are to be predicted. Okay, so it gives you. So if you have a balanced data set, this accuracy parameter works better for that. Okay, so we have a balanced data set here, so we've used accuracy. Okay, so MCC gives you an idea about the coverage. Okay, so how well the overall prediction has happened in both the positive and negative class. Okay, and the F measure is actually a weighted average about the precision and recall. So sensitivity or recall gives you an idea about the prediction in the positive class. So how well the interacting residues have been predicted, and the precision gives you, like say for example, you have an experiment, okay? The number of times you repeat the experiment, how many times has it come out well? So it gives you an idea of that. Okay?
So my question is about the volume of the data set. So I'm not sure about the healthcare domain. You told that there is 157 sequence which you
Right.
used. Once you convert into feature vector, it's like one feature vector per sequence?
No.
Okay.
It'll be like one feature vector per residue that we are considering.
Okay, so the overall data set, how did you ensure that the diversity of the overall data set is good enough?
Intact.
Yeah.
So as I told you, the data set is non-redundant. Okay, so we remove all the similar sequences that are already there.
Yeah, so you must have used some measures for that, right? Like how do you evaluate the diversity of your data set? Because if the data set is like really small, the machine learning algorithm which you are using might not be complete or it might fit.
We're looking at a very, okay, sorry, complete your question.
Yeah, so that's my question. Like, how do you ensure the diversity of data set? Because the data set is very small, because you have to be very specific about like you are including all the type of proteins or whatever you.
Okay, so
experimenting on.
I'm not sure if you've got the problem correct. We're looking at only one type of protein, which is mannose binding protein.
Okay.
So we actually do not want too much of diversity. There are only one particular class of proteins. They're similar types. So among them, whatever more similar, like if you have, say, for example, something which is 99% similar or 80% similar, we remove such sequences. We keep diversity so that not any sequence which is more than 25% similar to any other sequences.
But
any
then,
other-
then again, my question comes to like if the data set, all the data points are almost similar.
They're not similar.
Okay.
Okay, see, diversity in proteins is different. Diversity in the data sets that we have will be represented by the dissimilar sequences that we have among the mannose binding protein complexes.
Yes, okay.
Okay, so that
So
we are
your,
ensuring.
the way in which you make the metrics will capture that is what you're saying.
Okay, so what we are doing is we are checking all these sequences and we are using a server to remove the similar sequences. So any sequence is not more than 25% similar to the other sequence. We are ensuring we have diversity for this class with that.
Okay.
Okay.
Thank you.